Thank you all for coming today to this introduction to my arcological design research series. I'm very excited to delve into the arcological design principles to reify arcologies, of course, that I've been working on for the last 10 years. This will be part one of a multi-part series in which I will first go over in depth the conceptual basis for reifying these cities in a computer simulation and ultimately in real life, as well as the specifics of the programmatic environment and the variables and the requirements for life support logic within these city nodes. Without further ado, I'll go ahead and get right into it. An arcology is defined by its adherence to conceptual elements such as self-containment from its surrounding environment. An arcology may meet these conceptual and theoretical definitions by various means, the phenotype, as it were, of the assemblage being less important than the coverage of practical ideals. Moreover, the end-to-end resource intensity of the assemblage is given due consideration with regard to the nature of the relevant parts of the environment used to create and assemble the arcology in its initial build-out, as well as the ongoing maintenance requirements of the arcology taken together once it is in regular use. The specific environment used in the process of an arcological build-out would need to be well known and analyzed. That specific environment's resources, its existing ecological systems apart from the arcology, and generically the carrying capacity of that specific environment, as well as its geotechnical features, would be indispensable for any true calculation of the arcologicalness of a given architectural assemblage. We may take two definitions as most central to arcological planning. One, an arcology in its build-out as well as ongoing operation will preserve the surrounding environment and ecology while supporting its human population. Two, an arcology is self-contained in terms of resource flows. An arcology will produce and reuse all the material necessary to support its human population within its superstructure without drawing down from any external environment and without producing waste streams external to the arcology. These definitions are of the utmost importance when considering whether a given architectural assemblage is or is not a true arcology, and indeed, whether or not a given assemblage is a prototype testing arcological principles. Other arcological concepts, such as MCD, or miniaturization complexity duration, are certainly important and interesting. However, in practical terms, an arcology is mainly about being a city which relies on itself for its ongoing maintenance and operations. An arcology is like a gazelle, as Solari sometimes mentioned, lean, self-reliant, integrated ecologically into its environment, its grace, its elegance clear in its apparently simple form, yet made up of staggering biological complexity. An arcology is a hyperorganism. It shares many traits of an organism, the humans within the arcology, like cells within the human body, but it is more than an organism. An arcology is a manifestation of consciousness as much as it is a product of strictly ecological processes. A gazelle cannot determine before it is born what resources its body will comprise of and how they will be collected. Arcologists, the designers of an arcology, will have such benefit of foresight, overview, and planning. An arcology is indeed ideally a hyperorganism. However, humans have yet to fully cognize the extent of sophistication inherent to the range of biological life, as in cellular life. So to say hyperorganism, we are really reaching in terms of conceptual foundations. That is to say, it is understandable, but keeping in mind that humans do not grasp the depth, the sophistication, the material complexity, the durational intensity, the interconnectivity, the self-replicativity, and so forth of biological life as it stands, leave alone the expanded set of such life and its immensely detailed mechanics and capacity to sustain itself indefinitely via a myriad of forms interacting amongst themselves in a given planetary resource environment. When we consider the impact of energy to matter replication on arcological design, we broach the most central principles underlying the concept of arcology itself. That is to say, if very efficient energy to matter conversion, such as would produce edible food directly from electricity and some handful of stored elements on the periodic table, were made available, major urban planning challenges central to arcological architecture would be immediately addressed. This goes similarly for matter-to-energy conversion, i.e. the plasma arc gasification of organic waste streams, but perhaps not quite the same effect as energy to matter for food production, which is essentially magic to the current state of the art. Nonetheless, we can consider the impact of such technologies, even hypothetical ones, on arcological design, considering only our two primary definitions of arcology. Given the current state of the art of food production, one of the most interesting planning considerations for a specific arcology's design will necessarily be how food is produced within the arcology, how it is to be processed and transported to the cafe tables, and how organic waste will be dealt with once the meals have been consumed at said cafe tables. This food production system will be, by design, large enough to fully support the resident population of the arcology, with some significant margin in order to allow sustainable, permanent, closed system agriculture. We may look to the Earth's biosphere for insights into this design, as well as smaller parts of ecology, such as specific forests with well-defined trophic levels, predator-prey relationships, decomposers, and soil ecology. The size of such closed ecological systems may be significant, even staggering in scale, when considering what it might take to produce a truly self-sustaining food production system for a given large number of human individuals. That is, unless some aforementioned energy to matter technology becomes available, in which case the ecological dimensions of an arcology might be reduced to providing quality of life improvements. Given the current food production state of the art, we will begin our arcological simulation considering the extremely large CELSS, or Closed Ecological Life Support System, a contemporary arcological build-out would require. We will be taking the general conceptual framework of CELSS, modified for arcological research, not necessarily attempting to replicate any given lab's CELSS definitions or methodologies. Theoretical, arcological CELSS taken as a foundation, we might imagine a spectrum of correct solutions as part of an arcological design, broadly ranging from highly integrated closed socio-ecologies, or humans living amongst trees in a heavily forested starship arcology, for instance, to highly containerized, even physically separate, but architecturally connected closed ecologies, which serve to provide for a given society, but which are not generally interacted with in daily life. In summary, this set of formal definitions of arcology informs our programming environment for prototyping realistic arcological architecture in interactive 3D. These definitions will serve as a theoretical foundation for prototyping arcological assemblages and true arcologies in the computer simulation space, as well as provide a space to conceptually deal with arcological design in earnest. One of the clearest ways we can examine the relative efficiency of arcological assemblages is by comparing the centralization of eating spaces into shared cafes in an arcology to the more common practice of millions of individual and separate kitchens and restaurants as seen in conventional grid cities. This analytical comparison is complex, consisting of perhaps thousands of relevant variables. However, we can begin by performing a high-level analysis of the two categories of food procurement. In an arcological cafe space, we'd have a shared commercial kitchen scaled to feed n residents at the same time, shared trays and plates which are washed in a commercial scale dish room, storage of foodstuffs in a single location, preparation of foodstuffs in a single location, consumption of the prepared food in a single location, and on top of that, the ethnic and cultural varieties of food are unlimited in terms of what can be made in the cafe any given day. For comparison, in our conventional kitchens and restaurants, everyone has a separate kitchen. Everyone washes their own dishes separately with an individual sink and dishwasher. Everybody must transport themselves to the grocery store and back again. There is individualized packaging of foodstuffs before preparation, the individualized garbage production and recycling, which must be picked up at the curb for each person or resident, an arbitrary number of constantly changing restaurants, generically based on theme, like Italian or Mexican, each with their own separate kitchens. And everybody must transport themselves to an arbitrary number of restaurant locations if going out, as opposed to simply walking there. So, in a generic comparative analysis of intensity, an ACS, or arcological cafe space, again, that's ACS for our purposes today, there's one commercial kitchen built once, direct delivery of bulk foodstuffs to the commercial kitchen, no groceries, so no grocery stores. Bulk cleaning of plates, utensils, etc. in a central location, and everybody may walk to the location easily from their quarters or home. In comparison, here's CKR, or conventional kitchens and restaurants listed out. It would be, again, this is an intensity analysis, the population total times the individual kitchens built in times over the person's lifetime. The intensity of full cycle production, distribution for individual ovens, sinks, kitchen utensils, cleaning products, etc. for each individual kitchen space times the number of kitchens that individual will have over their lifetime. The intensity of the entire individual grocery store chain, like grocery store buildings, the construction, maintenance, utilities, parking lots, roads, individual cars, individual packaging instead of bulk packaging, and the intensity of arbitrary numbers of separate restaurants and their construction, maintenance, utilities, and kitchens. So some initial conclusions. ACS, or arcological cafe space, is wildly more efficient than CKR, or conventional kitchen and restaurants, likely by orders of magnitude. It would require an in-depth supply chain analysis to say precisely how much more efficient ACS is. However, we can consider some approximations. If the full cycle intensity of the conventional kitchen and restaurant lifestyle pattern per individual were accounted for, it might possibly equate to, per person, the intensity of the ACS build-out itself. That is to say, given the same energy and resource intensity of individual CKR, we could build ACS for some significant population total. So in terms of resource efficiency and the amount of labor required to sustain CKR, we might say that ACS is ACS initial build-out intensity times population total more efficient than CKR. Going a level deeper into the arcological efficiency analysis, we may consider the impact of producing the foodstuffs in large part or entirely locally to the arcological assemblage. These efficiencies, in terms of the full cycle intensity analysis, would be on top of the existing distribution and manufacturing efficiencies already outlined in our initial conclusions. In the CKR, conventional kitchen restaurant lifestyle pattern, which is our current day pattern, food production largely or entirely takes place outside of the regional area in which the foodstuffs are ultimately consumed. The well-known global transportation network of foodstuffs involves a huge number of vehicles and facilities, including ports, boats, planes, trucks, cars, tractors, vehicle lots, and so forth, in order to get the food to grocers and distributors all over the world. For ACS, we may consider fully localized food distribution, even to the point of effectively automating the process from greenhouse to table. Furthermore, with more intentional design of diets by some given arcological population, we might see extraordinary efficiencies in ACS, arcological cafe space, at the practical limits of design, particularly greenhouse-to-table ACS, which is built with the goal of extreme longevity in its operational design and maintenance. I believe this comparison underpins the systemic elegance envisioned in arcological frameworks, where shared infrastructure is harmonized to yield unprecedented efficiencies. The area of arcology studies, and specifically the visual representation of arcologies, has to date been done by artists rather than as part of a scientific methodology. Our effort is to build a conceptual framework which identifies the requirements for a true-to-life computer representation of arcology functions, variables, and interactions. The program function is to represent in code the multitude of variables prerequisite to the simulation of an arcology, to render such a city in an interactive game world, and finally, to allow extensions of the city generation logic to incorporate new or updated parameters. With regard to prior efforts, the Mars Colony Simulation, or MCS, which I built with Panda 3D, incorporates around 50 variables inherent to a realistic Mars dome, supporting a handful of exocolonists. This remains probably the most sophisticated program in arcology simulation. MCS is best studied as an example of how a multitude of city domain variables may be calculated to inform 3D modeling requirements. MCS would not be simple to scale to arbitrary requirements. It illustrates a minimal case of exohabitation in a functional style with highly specified 3D models. It reflects the true resource requirements for fewer than 5 exocolonists, showcasing an extraordinarily costly dome with technically infeasible air and vegetation requirements, and at a technically infeasible energy scale when considering the outer space environment and Mars gravity well. Indeed, the simulated dome greatly exceeds the size and agricultural capacity of Biosphere 2, unfortunately a largely failed $500 million Earth-based experiment in Oracle, Arizona. This information naturally begs the question of the overall feasibility on or off planet of arcology construction. MCS leaves out a fair number of manufacturing details which would be required to sustain life inside the dome, such as the processing of agricultural products, but it does attempt to minimally account for total energy losses due to conversion efficiency. There are several important things we can learn from the MCS. It provides a robust structure to compute dynamic life requirements logic for humans in a closed environment. It provides architectural requirements as delimited by air volume for closed ecosystems at 1 atmosphere of pressure. It provides various algorithms and data structures on a case-by-case basis, such as sun incidence per square meter. And finally, building the MCS provided practical experience by the nature of its first principles design. So what will have to be built where MCS left off? We will need generic abstract geometric primitives to be used as procedural stand-ins for to-be-defined architectural primitives. For example, the visible geometry of city generation minus aesthetics. We'll require the scaling of life requirements logic to fit large N population groupings. We'll need to record and load dynamic city specifications from external files. And finally, we'll require robust handling of city domain interaction dynamics of various granularity. Towards the end of MCS development, it had already become apparent that due to resource constraints inherent to real-time rendering on a PC, geometric abstractions of arcology functions would be beneficial. Such abstractions are also potentially less biased than more artistic, aesthetically opinionated structures when considering procedural layouts. The requirement for abstract architectural primitives is then a matter of performance, opinionation, and perhaps the reduction of artistic input. In the MCS, one can see large translucent green rectangular prisms, which are stacked upon one another in the agricultural area of the dome. These geometric primitives represent edible crop volume. The rectangular prism is the basis of the procedural stand-in. This shape, particularly in a translucent representation, seems well suited to illustrating the abstract layout of arbitrary arcology internal features. Progress in the visual representation of arcology simulation therefore depends primarily on defining which conceptual primitives, besides edible crop volume, must be calculated. Naively, defining a habitable volume for each arcology resident is tempting. However, it must be analyzed systematically what such volumes actually represent. In the range of all possible cities, many lifestyle configurations are potentially representable. If the resident's habitable volume is taken to be the sum of the resident's accessible, private, and public volume, much overlap between such volumes will become apparent. Even at this reduction, we must assume the distinction between private and public space domains, which may not be literal. It is hereby suggested that the public space domain is the principal domain space encapsulating private domain space. Such domain space should be calculated as a higher order reflection of subsystems rather than as external file input. Likewise, the domain space of goods final production intensity and goods final transport intensity may be delineated based upon manufacturing and distance factors. My previously published RBC, resource-based cities theory, suggests using minimax as a way to abstractly capture economic interaction between arbitrarily segmented arcological zones, should initial deployment intensity not capture end-to-end manufacturing and transport intensity. The distinction between a fully self-contained arcology and an RBC type arcology is thereby described with an associated self-containment factor. As of this year, the theoretical architecture for a fully self-contained arcological design for 150 residents, Dunbar's number scale, has been achieved in a computer simulation within the precepts described here today. Thank you very much.